Good evening and a very warm welcome to everyone joining us today. On behalf of IEEE branch chapter at KIIT and School of Electronics Engineering KIIT, it is my pleasure to welcome you all to today's online.
I cannot hear you. I can no longer hear you for some reason. Can you hear me?
We can hear you, sir.
Okay, now I can hear you.
Oh, all right, sir.
Something
So
happened.
we'll start again.
Okay.
All right, so we'll start again. Good evening and a very warm welcome to everyone joining us today. On behalf of IEEE EDS Student Branch Chapter at KIIT and the School of Electronics, it is my pleasure to welcome you all to today's online technical talk. We are truly honored to host Dr. Michael S. Shur, a distinguished authority in solid-state electronics and integrated circuits, who will speak on 100 years of FET, industrial phase of nanotechnology. Dr. Michael S. Schur is a globally recognized leader in solid-state electronics. He earned his MSEE from the St. Petersburg Electrotechnical Institute and his PhD and Doctorate of Science from the AFIOFE Institute. He currently holds Patricia W. and C. Sheldon Roberts Professorship at Rensselaer Polytechnic Institute. His pioneering contributions span semiconductor devices, FETs, and nanotechnology, and his work has significantly shaped modern electronics. A life fellow of IEEE and many other scientific societies, Dr. Schur has received numerous honors for his groundbreaking research and is widely recognized as one of the most influential scientists in the field, with an H index of 111 and recognition as a highly cited researcher. We are delighted to have him with us today. Thank you, Dr. Schur, for joining us. And thank you all for being here. We now look forward to an engaging and insightful session. Welcome. Over to you, Dr. Schur.
Yeah, thank you so much for this nice introduction. Thank you for inviting me. My special thanks also go to Electronic Device Society, IEEE Electronic Device Society. And what I would like to do now is to share the screen. Okay. Okay, can you see my screen?
Yes, sir, we can see your screen.
Okay, you can hear me, wonderful. So the title of my presentation, 100 Years of Field Effect Transistor and Industrial Phase of Nanotechnology. Well, first, I want to once again to thank Electronic Device Society that sponsors my talks. And this is a mission statement of this society to foster professional growth of its members by satisfying their needs for easy access to and exchange of technical information, publishing, education, technical recognition, and enhancing public visibility in the field of electronic devices. And it's a great society. It has many resources. It's truly international, and I'm honored to be a member of the society and one of the society lecturers, one of the society volunteers. There are over 20,000 Electronic Device Society members, 144 chapters worldwide, and please be a part of this community, either joining or simply attending online or in person, or whatever the lectures offered by Electronic Device Society. And now the outline of my talk. Well, field effect transistors are 100 years old. What's the exact data? Probably is debatable. But anyway, first I want to talk about how a field effect transistor works. Probably most in the audience know how it works, but still let me talk about it for a minute or so or less maybe. And then I will talk about nanotechnology and the field effect transistor. Because the field effect transistor and its modern incarnation took advantage of nanotechnology, achieving the ultimate scaling. This is an example of a device that uses, at least laterally, the surface, the shortest dimension among all commercial devices. And as a result of scaling to such small dimensions, the physics of electron transport, the physics of how field effect transistors operate, is very different from what we are used to and from we are still taught in many college courses, undergraduate college courses. It's different. And it's extremely important to understand this physics because its understanding has immediate practical applications. And without its understanding, you cannot be competitive in the field of field effect transistor technology. Then I will talk briefly about field effect technology evolution, how it progressed over 100 years. And this evolution hasn't ended. In the very end of my talk, I will say a few words. What could happen in addition to this enormous progress, enormous achievements? What we could expect? What are the competing ideas, competing technologies on the horizon? And one application of silicon CMOS with these tiny dimensions would be enable 6G technology, real 6G. I know that now even 5G is not fully deployed, but so maybe this prediction is too aggressive. But anyway, I think that it's necessary to switch to 6G, and I'll briefly talk about it. Why? And when it becomes real necessity, I think silicon CMOS technology, terahertz silicon CMOS technology, sub-terahertz silicon CMOS technology will be there. Well, one problem that is very important and that limits actual speed in your laptops and your desktop computers, whatever, is problem of interconnects. And I'm very proud to say that one of our faculty members at Rensselaer Polytechnic University, Professor Sheldon, has been instrumental in partially addressing this problem. It's not fully solved by any means, but what he proposed and what he has done, I think, has been revolutionary. And I will talk about some terahertz applications because I think that's where the future is, because of the 6G that will at the same time enable other applications in terahertz technology, and following by 10 topics. So how will field effect transistor works? Oh, before I really start, I want to say that if you want to interrupt me with questions, feel free to do that. Feel free. It doesn't bother me. And, I will be happy to try to answer your questions. It looks like internet connection is good, so I'll do my best to answer. So please do interrupt me if something is not clear or you want me to comment on it more. But anyway, field effect transistors are using semiconductor channels. The question, what is a semiconductor, is kind of an interesting question because so many materials that were considered insulators, like diamond, like boron nitride, are now considered having semiconductor properties. But what I'm thinking is that probably I could define a semiconductor like a chameleon of conductivity. So its electrical personality kind of changes by voltage, radiation, or atoms and or molecules in contact. So its ability to conduct electricity is governed by external excitations, by light, by impurities, by atoms deposited on it, by electric fields, by injector charges. So basically, ideally, what you could do, you could have semiconductor like a conducting material, the vehicle like metal conduct, or like a dielectric material. So it's a switch. It's a switch, and that's what is used in your laptop, where there's billions and billions of such switches appear. Anyway, if we consider a capacitor, two metal plates, electric field, constant electric field in the middle. And what is the difference between a capacitor and a field effect transistor? There are two differences. One difference is that the second plate is formed by conducting carriers, electrons or holes, at the interface between the electric and the semiconductor. So this is, you see my cursor, right? So this is the area that forms second plate of the capacitor. But these carriers have to come from somewhere, and they come from contacts, shown here in red, supplying these contacts into the channel. And then, let's say carriers are electrons. If I apply positive voltage, negative electrons are attracted to positive charges. So they will come into the channel and form a very narrow channel because they try to come as close as possible to positive charge. Well, it's like maybe a queen of, now king of England, visiting some city in Great Britain, and people want to see him, and they form a line and they come closer and closer, as close as possible to see the king forming that line. So electrons behave very similar way. And if I apply negative bias, they will be repelled and they'll go back into the context. So this is the principle of operation of a field effect transistor. First proposed file, patent file, October 8, 1926. So we could say that it's 100 years in 1925, or we could choose 1926, which is just a few months, short few months away, as a start of field effect transistor technology. And of course, in 26, 25, nothing happened. And it took so many years to actually implement field effect transistor and use it. Well, here's, I already taught how it operates. So that you have basically, you have here conducting channel in the semiconductor, the electric like gate, and strongly doped with ohmic contacts. And this barrier layer would be metal oxide semiconductor structure. So that could be silicon dioxide or silicon nitride. Instead, we could have a p-n junction, where the barrier is formed by the depletion layer, or Schottky barrier layer also formed by the depletion layer. We could have a heterojunction. And so there are so many different ways to implement field effect transistor. But the most important technology is CMOS technology, where you have on the same piece of silicon, you implement p-channel device and n-channel device. And if you connect this, maybe let's show a more realistic picture, more realistic picture. As you see, there are already complications. This picture doesn't look so simple anymore. But anyway, the principle is still the same, implementing the same piece of silicon. And if you now connect in series P and N channel device, then of course and apply voltage to the common terminal connecting the gates of the P channel device and N channel device. One device will be off, another will be off, depending on the voltage polarity. But basically, very little current, ideally no current will flow between drain and source. And as a result, it's a perfect switch. The most technology would be a perfect switch. And in 1958, Jack Kirby did something that was revolutionary, but extremely simple. Extremely simple. I'm sure that all of you in the audience could have come up with this idea on your own. Because all he did, he said, why use wires connecting P and N device, resistors and the field effect transistor performance circuit, where I could do it all in one piece of silicon. That's the entire idea that brings him Nobel Prize. Because of course the impact was tremendous. And this, from this simple piece, technology was developed by leaps and bounds and lead nanotechnology dimensions. What is nanotechnology? The definition is that the size is 100 nanometers or smaller. It's pretty generous because 100 nanometers nowadays is a very large dimension. And the first paper on nanotechnology, and one of these people, Alexei Alimov, got 2023 Nobel Prize in chemistry. Interesting, in chemistry. Maybe it should have been in physics, but he got it in chemistry. But they came up with the first paper on nanotechnology. And since that time, it really developed a lot. There are lots and lots of journals that primarily devote themselves to nanotechnology. There are many, many books in nanotechnology. And all these papers and all these books mostly represent the academic research. We academic researchers, we publish, we go to conferences, we're very noticeable. But a lot of work is done in companies like TSMC, Samsung, Intel, Global Foundry, and other companies, maybe AMD, whatever, many companies, by people who publish little, if at all, who rarely go to conferences, who are very bright, who work diligently and with great results. So they are basically, I will talk separately about their contribution. But now let's talk about nanosizes of integrated circuits. And the size that is now under research and development, technological size, is 1.4 nanometer. It means that it is smaller than proteins, much smaller than colloid gold, much smaller than bacteria by orders of magnitude or animal cell. And that, of course, means that you could implement very complex integrated circuits on a scale comparable to animal cell or human cell. And how small, of course, basically in 1980s, predictions were that this decrease in gate length, in the feature size, will stop for practical reasons at about 1 micron. And I came to field effect transistors for a different field. I was actually working on group theory. So I didn't know of practical limitations. So I started to consider what happens if device sizes are small, let's say 10 nanometers or smaller. And that resulted in the notion of ballistic transport. Because my simulation showed that you have, at such short sizes, electrons spend very little time, individual electrons spend very little time in the channel of filtering effect because they move with high velocities, thermal velocity or Fermi velocity. So they escape without even being able to experience scattering by phonons or impurities. And on longer times, they could be scattered by impurities and phonons, but without exchange energy, because to exchange energy, you need longer scattering time. And here, in this paper, I first focused on this region, so-called overshoot region. But soon I understood that this region here it basically is a function of distance, velocity changes the square root. That's a ballistic region. The electrons here behave like bullets, like free particles without knowing anything about scattering. So that started the notion of ballistic transfer. And what happened then? Basically, research in nanotechnology divided between industrial and research in academia and industrial phase. And industrial phase is now much more developed than research phase of nanotechnology. Both are very important, of course. Both are crucial. And possibly even maybe for most people, the research phase of nanotechnology is more interesting, but nevertheless. So where we are now, we came to the point where in Apple iPhone in 2015, 2016, 2017, 3 nanometer technological node is used. It doesn't mean the channel is 3 nanometers. The channel is probably more like 12 to 18 nanometers. But nevertheless, the minimum feature size is 3 nanometers. And this is had tremendous impact on silicon. There are other materials that were supposed to be competitors to silicon and overcome silicon and replace silicon. And as you see from this chart, actually, the gallium arsenide market developed quite nicely. It grew and continues to grow. So people who work on gallium arsenide have it good. But in terms of comparison between mainstream silicon technology, gallium arsenide technology, we are talking about orders of magnitude footprint in the market, many orders of magnitude smaller for gallium arsenide. And I will talk about why. So anyway, from simple ideas of living dark, many different implementations of technology have developed, and I will address some of them later on. But most important today is wraparound channel technology. When the gate is a tiny plate, the channel is a tiny plate embedded into the gate like this. And as I mentioned before, that's now not 18, 19. This is 3 nanometer technology in iPhone and used by literally billions of people. But it comes at the expense. This is how much it costs to build a foundry, up to $30 billion, which is depending on minimum feature size. But this is probably more relevant to this audience. It costs about $1.5 billion just to design a chip, not to fabricate, just to design. And what it means is that it's very important to understand the physics of such short devices in order to make an impact and reduce this enormous cost of technology development. And let me now talk about this counterintuitive physics of modern integrated circuits. Now, this, of course, very important, especially for the leaders in this technology, to understand and use it. But let me explain in more details what I'm talking about. These green balls represent electrons moving in a channel of a field effect transistor. They all move with the thermal velocity, or more likely with the Fermi velocity, which is on the order of 10 to the fifth meters per second, or even higher. It's a very large velocity. It's about only 300 times smaller than the velocity of light. So it's a very large velocity. And on this velocity, if we apply electric field between drain and source of field effect transistor, we superimpose drift velocity that is would be lost due to scattering with impurities of lattice vibrations. These red balls represent impurities, and these pictures represent lattice scattering. But there is a certain length that electron should travel in order to experience a collision with impurities lattice vibrations. So what if we make device shorter than this length? Then there's no scattering, no scattering. If you mean device much shorter than the mean free path, the scattering will not affect much electrons inside. You could say that the semiconductor became a superconductor. However, what happens, and well, first of all, when it happens, this is kind of an evolution. So it first happened in 2013, when Intel 15 nanometer technology actually had feature size below mean free path in silicon, even at room temperature. which is between 20 to 50 nanometers, depending on the quality of the material. And then it progressed even further. So basically, instead of collision-dominated transport, we have overshoot transport, and I talked about it, but also ballistic transport. This is simply this region blown up. And you see these parabolic curves that are typical for the free particle motion in constant electric field. So the first paper where we predicted such a transport was in 1979, and we tried to do some experiments showing that indeed we used diodes because it was easier to achieve such small dimensions in vertical devices. And basically we found a good agreement between theory and experiment. However, till 1999, so for 20 years, this concept didn't have many admirers. But in 1999, there was a paper published by Bell Labs. And at that time, 1999, Bell Labs was an authority in semiconductor technology. And people accepted the notion of ballistic transport. However, ballistic transistors, short channel transistors, they look pretty normal. Of course, this region where ideally there should be saturation, there's some figures show you that something is going on. And indeed, what happens, these transistors emit terahertz radiation. So they're not quite normal. Something is going on. And this radiation could be affected by the applied magnetic field. This B is magnetic field in Teslas. But what is going on is this. And that explains a lot why gallium arsenide hasn't been able to replace silicon. What people thought, working a lot on gallium arsenide for field effect transistors, they will be much better because it has higher mobility. Indeed, if you calculate response time as a function of mobility, like computer calculation, analytical calculation, but the trend is clear no matter how you compute it. That if mobility is higher, velocity is equal mobility times electric field velocity is higher, so device is faster, and material having higher mobility is better. But it's certain mobility value that strongly depends on the device size. The smaller the device size, the more this point shifts toward left. Okay, something happens. What happens? You reach ballistic limit, and you basically start oscillations of electronic fluid because electrons behave like a fluid in a conducting channel, and this is a ballistic mode of transport, and that we have to account for when you're in this regime. So basically, the effective mobility decreases actually when you start make device shorter beyond this point. So you have collision dominated regime. You also have viscous regime because electronic fluid is viscous. But this is a special topic beyond what we are considering today. So anyway, this is example of a 2-nanometer feature size. So you see, these are how many unit cells of silicon over 2 nanometers. And so depending how close they are to interface, they behave very differently. So you see the difficulties in order to maintain yield, because this structure should be really extremely sensitive to defects, and indeed lifetime decreases with the feature size, and reliability decreases with the feature size. So now the notion of the ballistic mobility. So what happens inside the device? which has dimensions much smaller than the mean FET, practically no collisions. It's a superconductor. But collisions occur when electrons hit the boundaries, the contacts, and that's where they lose the velocity. And this collision mechanism is the time of this mechanism is the dimension between source and drain divided by the effective velocity, either thermal velocity or Fermi velocity. So this is how it works. And basically, this is the expression for this mobility. And alpha is the effect of on the order of a unity that could be determined by solving the Boltzmann transport equation. But it varies little. Let's say from 1/3 to 2/3, something like that. And this is a calculation of alpha for different systems. Anyway, this is ballistic mobility. So the point is that once you make device short and very short, little depends on the bulk mobility. And everything is determined by the collisions with the boundaries of the channel. And therefore, for very, very short devices, the advantage of gallium arsenide compared to silicon is diminished. Now about experiment. This is the first observation in 2004 of the ballistic mobility vision. This is a much nicer paper, a much nicer MIT observation. You see the experimental point very, very close to the straight line predicted by the ballistic mobility theory. So understanding of these issues is extremely important for modeling field effect transistors. It's extremely important. And what happens? Our group worked a lot on developing usable models that could be implemented in ADS or SPICE or cadence SPICE for simulating individual transistors and simulating transistors implemented in integrated circuit. And what it required splitting the channel into many, many segments. And in each segment, the inductances representing electron inertia, capacitances representing mostly gate to channel capacitance. And also, not showing here, but also very important, resistances that are responsible for the losses. And of course, this is a great simplification compared to the real device parasitics. That's how it looks for more detailed studies of individual devices. So as you see, it's not an easy task. And there's a lot of work remaining for us semiconductor researchers, for you who are interested in this research, how to extract these parameters, how to develop a usable model. And what companies are using nowadays is called device technology for optimization, where up to 80% of effort into simulation, into trying to understand these effects and use simulations to design better devices. And our group develops a code named SPICE in order to solve this task. So let me briefly talk about field effect technology evolution. So typical technology, typical lithography, starts strictly below 2 microns because of optical attenuation. So now it's 1.4 millimeters. How did it happen? And that required many, many steps. Evolutionary scaling was down to 130 millimeters. After that, there are many other approaches using high K dielectric in order to scale the device appropriately. Using FinFET structure, using multi-bridge field effect transistors, and so on. And each step was extremely difficult to implement. As an example, I would say that Global Foundry, a few short years ago, got a contract from IBM to develop a 7 nanometer technology, not 1.4 nanometer, not 2 nanometers, not 3 nanometers that I use on iPhone, 7 nanometers. After spending about, in my estimate, maybe not accurate, about $1.5 billion, they failed and abandoned this effort. Abandoned. But anyway, making MOSFET, in addition to understanding physics, involves all those steps. And it's a challenge, it's a big challenge. And photolithography is still used to define the various patterns, but now it's UV photolithography and covered with some medium, usually water, in order to increase the index of refraction and make the resolution better. And using UV light, and this shows the steps in using UV light. And this is the machine that you have to buy. And I put myself as a ruler for comparing the sizes. So it's a big machine, and you probably could spend about $1 billion right there. Okay, so this is what I was already talking about. So it's a global foundry Abu Dhabi company, but very important for Rensselaer Polytechnic Institute, because one of the US campus is only about 10 miles, maybe 15 miles from the Rensselaer Polytechnic University campus. And this is how people achieved 90 nanometers and below using strained silicon. And no longer it's actually silicon. In modern devices, it's probably silicon germanium would be more accurate. And 65 nanometers required high K. Coaxial thin in fact idea, first proposed in this paper, was necessary to go all the way from 24 nanometers down to 7 nanometers. This is the representative of FinFET technology. And all-around FET also first proposed in this paper. Okay, that is something that works now up to 3 nanometers. Maybe it will work to feature size up to 1.4. Right? But there's an important problem. There's a problem of interconnects. See? And that shows the interconnect delay as a function of the gate length. And you see that even at 50 nanometers, this delay becomes larger than delay related to the transistor itself. Professor Shem Muraka replaced aluminum interconnects with copper. That was difficult because what was needed is to prevent contamination of silicon with copper. But he was successful in demonstrating that it could be done. And his contribution, I think, has been revolutionary because it really promoted the speed of modern CPU. Let us now talk about the uniqueness of this short channel CMOS technology, because I expect that if we're able to support terahertz silicon CMOS for 6G communication, maybe in short 3 years. This is what it's based upon. This is a log scale, and therefore what looks to you as a small increase beyond 5G capacity is actually a huge increase. So by 2030, even full 5G technology will not be able to support global mobile communication, and something will have to be done. Whether it's good or bad, I don't know. I don't know. I'm horrified seeing children looking at their phones and becoming basically experience maybe what I call digital dementia. But it's a philosophical question. Maybe it's too dangerous to develop better and better phones, better and better capabilities for social networks, for all that. I think it is dangerous, but probably not unavoidable. Probably nothing we can do to stop it. And technology will have to support what humans demand, and they have to support 6G capabilities. As you see from this slide, silicon CMOS have a potential to do that. Well, this is, of course, cutoff frequency. It's actual frequency on which circuit will operate. It's probably at least 1/3 of that. And this is not technological node. This is a channel size. So for 3 nanometer technology, that's probably what it is. But basically it shows that 3 nanometer technology is capable to operate at frequencies supporting 6G communication, like 150, maybe 200, maybe 250 gigahertz. That's of course extremely important. But there are problems. Some problems that you could probably work on and solve. Foundry models, when you design a circuit now, most of us don't fabricate anything. We just design the circuit using project development kits, design rules supplied by foundries, such as Global Foundry, for example, or others. And their models usually work up to 30 GHz, but maybe capabilities of silicon technology go to 300 GHz or higher. And for that, you have to not only use, but improve models supplied by foundry. And benefits of that you could dramatically decrease design cost, come up with more efficient, robust design, and develop sub-terahertz range using silicon technology. Now, technology is limited, terahertz applications are limited by high technology cost. To set up a terahertz, actually basic terahertz lab, will probably cost you about $200,000. But using 22 nanometer technology and the silicon technology, you could actually decrease the cost and address multi-billion market in terahertz communications, robotics, sensing, Internet of Things, security, biomedicine, education, industrial controls, site testing, and so forth. So let's talk about some of these applications. So this is terahertz applications mapped into terahertz range. And the most important one is this one. Once this is developed, probably at the maximum 600 GHz, maximum 600. Once it's developed, it will enable economical application in pharmaceutical technology, in monitoring Earth's atmosphere, in radio astronomy, in detection of explosives, and other applications. But today I want to talk about something because we talk about silicon transistors, about terahertz testing of radii. And what you see here is the plot of the number of transistors on chip. And we are reaching 4.3 trillions, not billion, trillions transistors. And these transistors are arranged in hundreds of thousands of CPUs on this piece, on this single piece of silicon. But many of these CPUs don't work because yield is not 100%. So it's very important when you deal with this technology to have non-destructive testing techniques in order to determine what's working, what's not working, what are the defects. And another issue, also extremely important, is the issue of hardware cybersecurity. So let me give you an example. This is Intel technology. Intel, up to 2017, was progressing so nicely, and was the first to demonstrate was something that was probably 10 nanometer technology. But what happened then? Okay, you see, Intel was in real trouble, and that shows that in our field, in the field of VLSI, you cannot be complacent. You cannot say, "Oh, I'm the greatest," because competition is there, new ideas are there. They might come from Europe, from China, from Taiwan, from India, from the United States. We don't know. But there are brilliant people working on it now. And maybe what's happening with Intel should be a lesson to us. And indeed, of course, it's difficult because this is what we are dealing with. This is showing all these really side layers. But interestingly enough, if you shine a terahertz beam, you could scan VLSI response and see voltages induced at the pins of VLSI. And that way, we could produce terahertz images of VLSI chip, not in one dimension, not in two dimensions, not in 3 dimensions, what human could see, but maybe in 10,000 dimensions. And use artificial intelligence in order to learn how to classify these images and what to do with these images. And this work has already started. Another important application beyond really side defects and reliability is hardware cybersecurity problem. This is a famous case of exploding pages. When all pages suddenly exploded, there was a very simple integrated circuit in there, but you see, tampering with that had consequences. And think about it. If you have billions of transistors in a laptop, how many transistors it would take to set up something that would monitor environments through the laptop camera, even when computer is off, because there's enough parasitic energy in space. Most could be collected, for example, from Wi-Fi signal, rectifying the Wi-Fi signal. And that would be enough, because for low power technology to achieve it. And this is an example of how terahertz radiation could indeed distinguish between fake and real VLSI. And this is an example of how it has been used in order to pinpoint. This is not for cybersecurity, this is for testing of VLSI, to pinpoint which transistor wasn't working in MMIC. Again, there's tremendous potential working in all that. So in conclusion, overcoming numerous technological challenges, industrial nanotechnology is reaching 1.4 nanometer technology now. This is tremendous progress over 100 years of field effect transistor. Astronomical cost of chip design should be reduced by counting new ballistic and plasmonic physics, because electrons form a plasma in the device channel and have resonant properties. And silicon CMOS technology could enable, should enable, I shouldn't say enables, should enable sub-terahertz technology for 6G communications. And questions and answers. But before I open to questions and answers, I want, as I promised, to tell you about what I have not discussed, and which is very important. It's tremendous technology we described, very powerful, used by billions of people in laptops and iPhones. But there is a technology that could challenge it challenging, that grows by leaps and bounds much quicker than CMOS technology. This is thin film transistor technology, especially metal oxides and thin film technology. Still a field effect transistor. Looking back in the future even more, there's work on still gallium arsenide based transistors. This research is continuing for showing record results. Nitride field effect transistors, diamond field effect transistors, graphene and 2D field effect transistors. And this technology are now not taken seriously enough. And indeed, there might be still years and years in development, but they have to be looked upon and could present serious competition to the mainstream technology I talked about. And now it's a good time for questions and answers. Thank you very much for your kind attention.
It was a really insightful talk, sir. So if anybody has any questions, Dr. Shur is open to it now. Sir, I'll ask my question then, since no one is coming up. All right. You mentioned that the industrial phase of nanotechnology is growing faster than the academic phase of it. Like, what do you mean by it? Like, what are the details?
Well, there is no academic lab that is capable of producing technology at 4.4 nanometer or even at 10 nanometers. Okay, so in terms of scaling transistors down, I think the leadership belongs to industry. It's not that you or other researchers couldn't contribute to it. You could contribute to it by developing good characterization models, by showing how to extract parameters, by predicting what would happen if you scale from 1.4 to 1.3 nanometer. I'm being facetious. But this is what I mean. I mean, they have achieved it. They have achieved. Industrial researchers, in my opinion, achieved this enormous technology advantages. Okay. Because, I haven't, since it's kind of celebration, I haven't seen a few slides that show how dramatically lifetime and reliability drop when you scale down. So basically, my iPhone, my recent iPhone, lives already 2 years. This is great. This is great. How did they achieve it? I don't know.
Sir, is this the case with all the engineering industries as of now? And by the way, if industrial phase is moving faster than academic phase, why did you choose to remain in academia?
Well, actually, on my fly, you say professor. I'm still a professor emeritus. I accepted position as the president of a startup company. The company works on terahertz testing of VLSI and some things like that. And the technology is great, it's working, but it's very, very expensive. That's what keeps that's what keeps the company down. Another thing that sometimes people don't want to find out how reliable the devices on integrated circuits are. That's another obstacle. But anyway, the company is alive, doing okay. But I also remain a researcher at RPI. I keep my lab. But I no longer teach, except for lectures like this. So I'm kind of shifting from industry. And also in the past, I had a bunch of companies that I founded and co-founded.
Does anyone else has any questions? Okay, for all the attendees, the attendance form will be posted in the chat box in 2 to 3 minutes. All right, sir. So since we